we tasked ourselves with asking the question, what is the source of statistical uncertainty? And I think both the Bayesian and Frequentis can agree that statistical uncertainty arises because we've only observed a finite sample from a potentially infinite population. And so our argument is that actually what we need to know any parameter of interest is this entire population, y1 to infinity. And so in our work, what we do is we argue that the source of Bayesian uncertainty is precisely the remainder of this population that we haven't seen yet. So we've seen y1 to n, we still need yn plus 1 to infinity to know the parameter precisely. And so in our work, we actually view Bayesian inference as a type of bootstrap-like scheme, where given the parameter, given the observations y1 to n, we're going to view Bayesian posterior sampling as shown here. So there's going to consist of two steps. The first step is to actually impute this remainder of the population, yn plus 1 to infinity, from our joint predictive density. Then given that we've seen this entire population now, yn plus 1 to infinity, including y1 to n, we can compute any parameter of interest precisely. So that's shown here in the second line. And so the kind of high-level idea is that the Bayesian actually imputes what they need to know the parameter, which is the remainder of the population, yn plus 1 to infinity. And there's a really nice connection shown by Doob's consistency theorem that if we specify p of yn plus 1 to infinity as the Bayesian posterior predictive density, and also specify the parameter of interest as, say, a consistent estimator like the maximum likelihood, then the parameter will be distributed according to the posterior. So here's sort of the view on this in a more diagrammatical way. So consider a finite population of size capital N. We have n people in this population, and we take three measurements A, B, and C. And suppose the parameter of interest is some function of A, B, and C. For example, we want to know the population mean of A. Now, when we carry out a study, what we do is we draw a few samples from this population. So in this case, we've drawn person 1 and person 4, where everyone else is missing. And so under the assumption of exchangeability, then, we can assume that person 1 and person 2 have been observed, but person 3 to capital N have yet to be observed. And what we show in our paper is that what the Bayesian carries out is something we call predictive resampling, which is to repeatedly impute the remainder of the population, persons 3 to capital N. And every time you do this, you can then compute a new parameter of interest since you've basically seen the whole population. And the distribution of the parameter is specifically distribution. So on this slide here, I'm going to introduce an algorithm called predictive resampling. Predictive resampling is essentially a way to carry out this imputation in a computational way. So we're going to denote the predictive I plus 1 as p subscript I. And what we're going to do is we're going to have the sequential imputation algorithm to draw density p of yn plus 1 to capital N. And in this case, we're going to be using this factorization, this chain rule, essentially, to compute the joint predictive density. So following this, one is to compute Pn from the observed data y1 to n. And then what we're going to do is for each of the capital B posterior samples, we're going to carry out a for loop. We're going to start at I equals n, n plus 1. So what we're going to do is we're going to draw yn plus 1 from our predictive density. This is just going to be sampling from our model. What we're then going to do is we're actually going to update our predictive density. So we're going to compute pi, which is going to be a function of this new simulated data point as well as the old predictive. And we're going to repeat this over time. And you can show that this is equivalent to sampling from the joint predictive density shown in the area above the algorithm. And finally, at the end of this, we're going to compute some parameter of interest, which is going to be a function of this imputed population. And so now I'm going to go through a parametric example step by step to show what this looks like in practice. Of course, we're going to start with a very simple normal likelihood and prior, where from conjugacy, we know that the posterior density takes on the form here. It's a normal density where the mean is going to be roughly the sample average with this extra plus 1 term from the prior. And the variance is going to be proportional 1 to 1 over n, again with this plus 1 term in the prior. Then we know that by integrating manually, the posterior predictive density takes on the form here. So this is the normal density with mean theta bar n and variance 1 plus sigma bar n squared. And what we're going to do is we're going to carry out predictive resampling. So let's suppose we started with this predictive density directly, this normal density with theta bar n and 1 plus sigma n squared as the variance. We're going to draw yn plus 1 from this predictive density. We're then going to update our predictive as if yn plus 1 was one of the observations. So theta bar n plus 1 is simply going to be the sample average of y1 to n plus 1. And the variance is now going to be 1 over n plus 2. And we're going to repeat this onwards to infinity. And so on this slide here, I've run a little simulation to show what that looks like in practice. So suppose we've generated, say, 10 data points from some underlying sampling density. In this case, theta is equal to 2. And our estimate of theta bar n is going to be 1.84. And what I'm going to show here is that Doob's theorem shows that the two predictive resampling scheme is going to be the same as sampling from posterior. So on the figure on the left here, we have sample trajectories. On the x-axis is going to be the number of forward steps that we've imputed, whereas on the y-axis, we're going to be plotting these trajectories of what the sample average, so essentially an estimate of theta n is turning into. And so as we forward sample, we can see that the posterior mean, or in this case, just theta bar n, is going to converge to these values. And the reason why it converges is because we're imputing the whole population. So eventually we've seen everyone, and we know that the population mean is going to be equal to this value. However, every time you run this new predictive resampling scheme, we see that the parameter of interest converges to a different location. And if we plot the kernel density estimate of where theta bars converge to, we can see that indeed the limiting distribution of this estimate from the imputed population is going to be exactly the same as the posterior density here. And so now we're going to generalize. We're going to break free from the traditional likelihood and prior framework. We're actually going to consider a more general sequence of one step ahead predictive densities and a more general parameter of interest. So in this case, we're essentially replacing likelihood and prior specification with the specification of the sequence of one step ahead predictive densities from time n+1 onwards. I'm not going to go into this martingale condition too much in this talk, but in the later discussion meeting, I'll discuss why it's a really good idea to make sure that the predictive densities have to satisfy a martingale condition. And so the first step is, of course, to carry out predictive resampling, as we've done before. What we're going to do is we're going to sequentially draw yn+1 from our predictive density, update, draw yn+2 onwards until we have the imputed population, noting again that the first n data points are fixed because we've seen the data. Then we're going to compute some parameter of interest from this infinite population. We formalize this a little bit more in the paper, and I will talk about this in the discussion meeting. But for now, you can just think of it as essentially some kind of function of this entire population, like the population mean or the population median. And in practice, you can actually do this for a large but finite capital N, and we can show that actually this converges to the right thing. And so the Martingale Posterior distribution framework is going to consist of these two steps. And what's really interesting, at least in our view from this framework, is that it encompasses a few really interesting use cases and also gives suggestions for new specifications of models. So firstly, of course, we know that if our one step ahead predictive density is the Bayesian posterior predictive density, and our parameter of interest is that indexing the sampling density, where you can estimate it, for example, through a maximum likelihood estimate, then we know that the distribution of theta is the same as the Bayesian posterior. We're now going to talk a little bit about an interesting case where we elicit this one step ahead predictive distribution to be the empirical distribution, which is pretty familiar for those in frequentist nonparametrics, for example. And we're going to see that this recovers the Bayesian bootstrap. And then finally, at the end, we're going to talk about how one can elicit a more general sequence of one step ahead predictive densities, which satisfy some notion of this martingale condition, which is one of the weaker conditions that we need. And we're going to recover this martingale posterior. And we'll see later on that the bivariate copula is going to be a really useful tool. And this is going to be a proper generalization of the Bayesian framework. So now I'm going to talk a little bit about the Bayesian bootstrap. For those who are unfamiliar, I'm also going to give a little animation to see what it looks like in practice. And then I'm going to use this as kind of a benchmark to compare Bayesian and frequentist uncertainty, which I think sheds light on the different notions of uncertainty that we're interested in these two fields. So we're going to start off with eliciting essentially the simplest non-parametric predictive. This is going to be the empirical distribution. So essentially what we're saying here is that the probability of observing yn+1 is just going to be 1 over n equals spread over the data points we've already seen. And so what predictive resampling involves repeating now is to first we draw yn+1. And because we're drawing from the empirical distribution, of course, it's going to be a repeat of y1 to n. What we're then going to do is we're going to update our empirical distribution, treating y1 to n+1 as the observed population. So now we're going to have the empirical distribution over y1 to n+1. And of course, as I mentioned before, when you carry the scheme onwards, we're going to see that the drawn yn+1 to infinity will just be repeats of the observed data points. And the key connection that we make here is that if we carry out this predictive resampling scheme and under the framework of the Martingale Posterior with the empirical distribution, this is exactly equivalent to the Bayesian bootstrap, which was introduced by Rubin in 1981. So if we now cast the Bayesian bootstrap as this predictive resampling framework, we're going to see that what ends up happening is you draw these n Dirichlet weights, and our limiting empirical distribution, f infinity. So I won't go into the details too much, but f infinity essentially represents now our imputed population is going to be a weighted sum of the empirical distribution where the weights are coming from a Dirichlet with a flat alpha. And then we're going to compute some parameter of interest, which is a function of f infinity. Again, this is the same thing as computing a function from y1 to infinity. And so the Bayesian bootstrap is really neat. Aside from this connection, actually, the Bayesian bootstrap has already been investigated independently and shown to have really good properties under model specification because of its connections to the Dirichlet process and Bayesian non-parametrics. There's also been some recent work to show that under large data settings and complex models, the Bayesian bootstrap is particularly fast and parallelizable and can handle some level of multimodality. However, of course, we know that F infinity in this case is going to be discrete at the data points that we've seen already because our predictive is going to only have support on y1 to n. So this is going to be problematic if our parameter of interest requires some level of smoothness. For example, if we're interested in the density, then this isn't really going to work. So now I have a little animation for those who are unfamiliar with the Bayesian bootstrap. So on the top left, we have, let's say, 10 data points from a simple regression problem, and we have x, y pairs. And the parameter of interest is going to be essentially the linear model, which minimizes the least squared error. So in this case, in the gray line, we have this maximum likelihood estimate, or the least squared error, which goes through the blue dots. And what the Bayesian bootstrap does is because it's going to draw random Dirichlet weights, shown on the bottom left, and it's going to essentially reweight each of the observations when fitting this maximum likelihood estimate of the slope and the intercept. And then we see here that every time we draw this sample of w1 to n, the red line is going to bounce about, and we're going to get a random sample of beta and gamma, which is the intercept and the slope of the linear model. And then we can see here that this is going to be drawing samples from a posterior density from the Bayesian bootstrap. So now I'm going to use this as a benchmark to compare Bayesian and frequentist uncertainty. Of course, there's already been seen that there's a lot of overlap. We're going to be drawing, for example, Dirichlet weights instead of multinomial weights. But we're going to be viewing this from a predictive sampling point of view. So for the frequentist, what one does is models the underlying distribution as the empirical distribution, and we're going to draw n repeats from this population, y1 to n star, without any idea of updating. This is going to give us a random data set, y star 1 to n, and then we're going to compute the estimate theta as a function of y1 to n star. On the other hand, the Bayesian bootstrap is going to draw this population yn plus 1 to infinity from the joint predictive implied by the sequence of empirical distributions, giving us a random complete data set y1 to infinity from which we compute our parameter of interest. And so this formally highlights that actually Bayesians and frequentists look at two sides of the population. The Bayesian considers the uncertainty in what we haven't seen yet, yn plus 1 to infinity, and computes actually the estimand when carrying out the bootstrap. On the other hand, the frequentist is interested in what could have happened, and so they're going to be looking backwards in time and considering different values that y1 to n could have taken, and as a result, the implied distribution on the estimator theta bar. And what we think is nice is that both methods only specify the empirical distribution, and they both carry out some ideas of resampling. But the key here is that for us to look at the Bayesian bootstrap in a Bayesian way, we didn't actually need to specify a prior distribution in any of this. Of course, there might be an implicit prior distribution, but the point is that we started off with the predictive. We started off with pretty much the same thing as the frequentist bootstrap, and we just carried out resampling in a different way. So as promised, I'm now going to go through some new methodology. This is going to be essentially extending the Bayesian bootstrap to the case of continuous densities, and we're going to be using this bivariate copula update, which I think has a nice interpretation. And then at the end, I'm going to demonstrate what this looks like. So I'm going to demonstrate an example where we can actually do Bayesian density estimation without a likelihood or a prior. And so the bivariate copula update is an update introduced by some work by Han et al. In 2018. So the idea here is we're going to consider a recursive update shown here. So again, showing p subscript I is the predictive density given y1 to I. In this case, y is just going to be some arbitrary test point, potentially on a grid. We're going to consider the recursive update where we take this predicted density, and then we're going to see a new observation yi plus 1. And to get our updated predictive density, we're going to take some function of those two things. And what we're actually going to use here is some bivariate copula update, which is really nice because it ensures that the Martingale property holds. So the fact that it's going to be coherent is guaranteed. And so specifically, the bivariate copula density is actually a bivariate density with uniform marginals. And what's really nice about the bivariate density is it models essentially dependence between two inputs. And so specifically, we're actually going to be using the update shown here. There's a lot of derivations that can go through it, but essentially this is an update that's inspired by Bayesian non-parametrics. What we're going to have here is we're going to have the new predictive density is going to be a weighted sum of the old predictive density and this copula term times the old predictive density. I'm going to plot this on the next slide to show you that it looks very much like a kernel density estimate, where here C is going to be a Gaussian copula density, and our weights are going to scale order n to the -1. And then here we also have a bandwidth from 0 to 1. So I'm going to illustrate what this looks like on the next slide now. So as I said before, this update can be interpreted as a kernel density estimate. What we're doing is we're taking a weighted sum of the old density and adding essentially a kernel centered around this new data point, yi+1, where rho is going to be our bandwidth term. And so on the figure on the left, we see here the gray dotted line is the old predictive density. And we've seen this new observation, yi+1, and we want to update our predictive density given this observation. And so on the right here, we can on the left figure, we can see that in solid, we're going to have this term C of uv times pi. This is going to be the right-hand side of the equation, which is essentially a kernel centered about this new observation, yi+1. And as we increase the bandwidth from 0.7 to 0.9, we can see that the kernel gets more and more peaked about this observed data point. And the other thing I want to highlight here is that actually the kernel for lower levels of bandwidth isn't centered at the data point. It's actually regularized somewhat towards pi. And this interpretation is quite nice. What it's saying is that we're using a kernel density estimate, but the kernel is going to be data adaptive. It's going to be somewhat shrinked towards the prior. And as we increase the bandwidth, the shrinkage gets smaller and smaller. And when we take a weighted sum of the old predictive density and this Gaussian copula term on the right, essentially what we have is on the right of figure 2. So we're going to have the dotted line is going to be the old predictive density. And we're going to take a weighted sum of the old predictive density and the kernel. And that's going to give us the classic bimodal density with a peak on the new observed data point, where the peakness is essentially governed by this bandwidth rho. And so actually predictive resampling is computationally quite simple with this Copula method. Again, I'll go through the details in the discussion meeting, but the idea here is that because our update is inherently recursive, we don't actually have to do expensive model refitting. It's going to be a very quick procedure. And just for reference, we can carry out predictive resampling with the Copula methods in about 2.5 seconds. This is carried out on a GPU, which helps with parallelization, whereas when we carry out the Dirichlet process mixture model, in this case, we had to do Gibbs sampling, which took about 20 seconds. So this kind of scalability doesn't necessarily generalize to all settings, but it shows that it's definitely viable to carry out this predictive resampling. So on the figure of the left, in figure 3, we have essentially a comparison between our Copula predictives and predictive resampling with the Dirichlet process mixture model. This is going to be on the Galaxy data set where we have 82 data points. And we can see here that in this plot, the solid line is going to be the posterior mean for both the Copula method and the Dirichlet process mixture model. And the gray bands are going to be the 95% credible intervals capturing the density. And we can see that, of course, the plots are a little bit different, but the posterior mean follows a very similar shape. And the variance is slightly higher for the Copula, but it has the uncertainty in the same regions. And of course, given this Martingale posterior sample of essentially the limiting empirical distribution, in this case, we're actually going to be considering the limiting predictive density. You can show that it's the same thing. We can then compress this into any parameter of interest, d to infinity, as we described previously, step 2 in the Martingale posterior. So we may be interested, for example, in the number of modes in the limiting density, and we're also interested, for example, in the quantiles. So on the figure on the left here, we have a plot of the posterior of the number of modes. In dark, we have the Copula update, and in white or gray, we have the Dirichlet process mixture model. We can see that the Copula method actually prefers 4 modes, whereas the DPMM prefers 5 modes. And then on the right, we also have a plot, a posterior density plot of the 10% quantiles. Of course, we get a random density at each posterior sample, so we get a random quantile. And we can see that, again, the distributions are somewhat comparable, but once again, a little different. So now I'm going to provide some conclusions to wrap up what I just went through. And so in conclusion, our paper presents some new foundations, we think, about Bayesian inference. We motivate Bayesian inference now as imputing yn+1 to infinity with this joint predictive density. And this is what induces uncertainty in any parameter of interest. This, of course, holds in both the parametric Bayesian case, the non-parametric case, and our generalization to Martingale posteriors. We found that the bootstrap interpretation is particularly insightful. We can view that Bayesian uncertainty arises from this remainder of the population, whereas the frequentist uncertainty arises from the other side, y1 to n, and there's no necessary specification of prior here. And we also introduced some new methodologies. So we think about generalizing Bayes by considering a more general class of predictive distributions instead of that implied by the Bayesian model, and more general parameters of interest. And now we can get proper non-parametric Bayesian inference without the specification of the likelihood in the prior. And finally, we found that the bivariate copulas is a particularly useful tool here to ensure our updates are coherent. We actually extend this copula methodology for multivariate density estimation and regression in the paper. And of course, we hope that there's going to be an even bigger class of models that can be used in this context. So thank you for your time. And on the next slide, I have some references.
Does anybody in the audience have? Go ahead.
So I'm not a Bayesian, so this may be the realm of silly questions, but I'm going to ask anyway. So in your little example where you started with a 1/n weight on each of the observations, and you sample one of your observations, you then get, then you move to the next one, and you do an update. You then have one observation that has a weight of 2/n.
Yeah.
All the others have an observation of 1/n. So if I now draw from that distribution, I'm more likely to get the same one again.
Yeah.
So why doesn't that process run away? And why does it converge to a nice distribution that you want?
That's a good point. So while it does happen that you're more likely to draw yn plus 2, the minute you don't draw that, which is going to have a higher probability, right? Like you're more likely to actually draw one of the other atoms. You're now going to be on even playing ground. 2 of your data points are going to have weight 2. And so what's really neat with this poly-Ern scheme is that it kind of balances itself out because you're much more likely to draw one of the other atoms. And eventually you end up with a random weighting, which is distributed according to the Dirichlet. Somewhat peaked, but still, on average equal to the uniform distribution. So it's pretty interesting. But I never thought of that. It's really interesting.
I have a question about in a copula, you have a row parameter.
Yeah.
So you have to presumably choose that.
Yeah.
I was going to ask about the interpretation. So is that part of the implicit prior, or is it more like a tuning parameter like a random walk or something?
The row actually, so the technical detail is that it actually comes up as like a hyperparameter. It's a function of a few hyperparameters. So in the Bayesian non-parametric model, for example, you might have a prior on like the location. It's actually like a function of the variance. So it's like how tight you think your prior is on theta. But then when we carry out actual inference, you can learn this as a usual hyperparameter like you do in empirical Bayes. We can maximize, say, some version of the marginal likelihood, and then set the row to basically fit well with the data. So it's very much like a hyperparameter in the prior.
Okay, please. No. Okay. Well, thanks everyone for attending online. Thanks everyone for attending in person. And the discussion meeting, somebody says thank you. The discussion meeting will be at 5. I hope many can join us then. Thank you very much. And let's thank the speakers then.